Welcome to our first video on finite math. Let's take a quick look at what finite math is all about. So finite math is a collection of real-world applications that build on Math 11. We can do a quick course overview here and just get a sense of what kind of topics we're going to be looking at in the course. So first topic, chapters 3 to 5, we'll be looking at probability. We're going to look at a variety of different situations, and in each situation, we'll ask, is an event likely to happen, unlikely to happen, or somewhere in between? From there, we'll look at chapters 1 and 2 and cover a topic called linear programming. Linear programming is all about making a quantity as big as possible or as small as possible when there are some restrictions in play. So just to think about a typical example, that could be something like, imagine you're looking at a manufacturing company. You could be asking, how can we maximize profit if we have a fixed amount of capital and raw materials to work with? So here you're trying to maximize something, i.e. the profit, and you've got some restrictions, like you've only got a certain amount of capital and raw materials to play with. So those are the sorts of questions that we'll be looking at within linear programming. From there, we'll move into chapter 6 and 7. We'll be looking at two topics called matrices and Markov chains. Markov chains are all about long-term prediction. So just as a typical example of something we might look at there, we could be focusing on a specific company and maybe we want to predict the company's market share 5 years from now. So those are three major topics in the course, and then from there we finish the course with two short topics. Chapter 8, all about financial math, and Chapter 9, logic as it applies to the real world. Throughout the course we'll focus on applications as much as possible, try to relate this to the real world and to your future professional lives. And throughout the course we'll look at applications to business, to social science, and to health science. So with that, we're going to jump into our course content and start to focus on chapter 3, where we're getting ready to talk about probability. So we're starting off with section 3.1, talking about sets. So a set is a collection of objects called elements. Let's do an example of some sets. We'll do 3 examples here. So when we talk about sets, we usually give them a capital letter name, like capital A, capital B, capital C. And we use set brackets just to indicate where the set is beginning and ending. So the set A has 3 elements, X, Y, Z. And we just put these curly set brackets around there just to make it easier to read our set. Now let's say set B is the set of all odd numbers between 2 and 10. So you could rewrite that set more explicitly, and you could just actually list which numbers are in that set. So all the odd numbers between 2 and 10, that would be 3, 5, 7, and 9. And we just put our set brackets at the beginning and the end there. So it's equivalent to describe B like this in words, or to say set B is the set 3, 5, 7, 9. Third example of a set, we could say set C is the set of possible outcomes from tossing a coin twice. So when we talk about tossing coins, what we really care about is whether we're getting heads or tails. So let's just come up with a shorthand notation here where capital H means heads, capital T means tails. And let's think about what could happen if you take a quarter, let's say, and you toss it twice. Well, one thing that could happen is you could get heads and then heads. Another thing that could happen, heads then tails. You could see this the other way around where you have tails and then heads, or you could see tails twice in a row. So there are 4 different elements in this set, just representing what the possible outcomes are when you toss that coin twice. Now we're going to look at a couple of operations that we can perform on sets, and once we've defined these, then we can jump into some bigger examples. So first let's talk about the union of 2 sets A and B. The notation we're going to use for this is just the symbol U for the union. So we'll write AUB or A union B. What that represents, it's the set of elements that belong to A or B or both. So you're just grabbing everything that's in A, grabbing everything that's in B, throwing all those things together, and that produces your union. So key word that I always think about when we're talking about union is or. All the things, all the elements that are in A or B or both. Second set operation we can talk about is the intersection of two sets A and B. And we're going to write that using an upside down U. So it looks like this. When we read this symbol, we say A intersect B. So the intersection of A and B, it's the set of elements that belong to A and B. So it's a set of elements that are in both sets. And if we want to write down a keyword here, we could say and is the keyword that we're going to think about for the intersection. So all the elements that are in both A and B. So here we have two sets A and B, and we're just going to practice our two operations. So let's start with the union, A union B. We want to write down all the elements that are in A or B or both. So one way to do that is just to copy out everything we had in A. So -3, -1, 1, 3, 5. And then we can look through the set B and throw in any elements that we haven't already written down. So the -2, we haven't written that down yet. -1, we've actually already got that covered, so we don't need to write that down again. The 3 has already been written down, and then we have a 4. So there we go. That's A union B, all the elements that are in A or B or both. Now, when you're writing sets down, you don't list an element twice. So notice that when we were writing this down, the -1 appeared in both sets. We didn't write that down twice. So you never need to repeat elements within a set. The other comment I would make here is that order doesn't matter when we're writing down our elements. So one person may have given their answer the way we gave it here. Another person might say, oh, I think this would look better if I just reordered it. So if we reordered it and put it in numerical order, you could say -3, -2, -1, and then 1, 3, 4, 5. That would be totally fine. So these sets are equal. Order doesn't matter when you're writing down sets. Now let's practice our other operation, which is the intersection operation. If you want a keyword here, you can think and. So we're just asking which elements belong to both A and B. So one way to do this is just to go systematically through the first set and ask, is that element in the other set as well? So first thing we see is -3, that's not in B. So that does not belong to both sets. -1 does belong to both sets. +1 does not belong to both sets. 3 does belong to both sets. And 5 does not belong to both sets. So there we go. We've gone through that systematically, and now we know we haven't missed anything. So it's just -1 and 3 that belong to both sets. Therefore, A intersect B, -1 and 3. So here we have 3 sets, and we're going to do a more complicated operation here. The key to this kind of problem is just to think order of operations. We want to start inside the brackets. So if we could first figure out what the set A union B looks like, we'll do that first, then we could do the intersection operation with C. So just work inside the brackets first. A union B, we're thinking of or as being the keyword, and we're just listing out all the elements that are in A or B or both. So that would be 1, 2, 3, 4, 5. Now that we've got that, we can think about taking this set, A union B, and intersecting it with C. When we do the intersection operation, and is the keyword. So now we want to write down all the elements that are in A union B and that are also in C. So in other words, you're just figuring out what do these two sets have in common. Well, let's highlight the set C, and we'll also highlight the set A union B. What do these guys have in common? 1, 4, and 5. So there we go. Okay, let's modify this problem a little bit. Let's make C look a little bit different. And we'll try a second version of the problem. If C is the set 0, 1, 5, 6, then our set A union B still looks the same as before. Nothing has changed there. But let's think about how the intersection now changes. So we're looking at A union B. We're looking at the set C, and we're asking, what do these two sets have in common? Well, now it would be 1 and 5. So 1 and 5 are the elements that belong to both A union B and C. Time for another definition. We say that set B is a subset of a set A, and we use this notation here. It's like a C with a little line underneath it. So B is a subset of A if every element of B is contained in A. So you can think of this notation here as meaning B is contained in A, and the line underneath the C indicates that the two sets are allowed to be equal. But properly we read that as B is a subset of A. So let's look at a few quick examples of using this notation. So we could say the set 1, 3 is a subset of the set 1, 2, 3. So what we're looking for is that everything over here is contained in the second set. We could say that the set 1, 3 is a subset of itself. That works. A set is always a subset of itself because everything in the first set will definitely be contained in the second set. So remember that sets can be written in any order. So the set 1, 3 is a subset of the set 3, 1. And if you want to show that something is not a subset of another set, you could say the set 3, 4 is not a subset of the set 1, 2, 3. So you just put this line through the subset operation to indicate not a subset. You could read that as the set 3, 4 is not a subset of the set 1, 2, 3. Now let's define the empty set. The symbol we're going to use for the empty set is this. It's like a 0 with a slash through it. The empty set contains no elements, and it is a subset of every set. So let's do a quick example here just to practice these properties of the empty set. If you take the set 1, 3 and you do the intersection with the set 2, 4, there's nothing in that intersection. There are no elements that belong to both the first set and the second set. So the way that we write that in set language is to say this intersection is equal to the empty set. So the empty set is just used to represent a set that has no elements in it. The empty set is a subset of every set. So we can say the empty set is a subset of the set that just contains this number 1. The empty set is a subset of the set, let's say 1, 2, 3. And the empty set is also considered to be a subset of itself, since we said the empty set is a subset of every set. So let's see if we can list all the subsets of the set X, Y, Z. Well, if we do this systematically, I would say a set is always considered to be a subset of itself. So we've got one subset that has 3 elements in it. And then there would be a few options of subsets that just have 2 elements. So you could grab X and Y as one of your subsets. You could take X and Z, or you could take Y and Z. So those would be all the options of subsets of our original set that have 2 elements. Then we could start to think about subsets that just have a single element. So you could take just the set X, or the set just containing Y, or the set just containing Z. And then there's one other subset that we haven't listed yet, probably the easiest one to forget about. That is the subset that has no elements. So that's where the empty set comes into play. So there are 8 subsets of our original set X, Y, Z. As we're going through all of these definitions and examples around sets, I want us just to remember that what we're doing here is just preparing ourselves to get into a discussion about probability a bit later on in this course. And sets are the language in which that probability discussion happens. So now we've got one more set operation to look at. We're going to talk about the complement of a set A. The way we're going to write that is A with an apostrophe beside that. So complement of A. It's the set of all elements in the universal set U that are not in A. So key word we want to think about when we talk about the complement of a set is not. And let's jump into an example. We'll see what this universal set is all about, and we'll see exactly how to calculate the complement of a set. So here we have a set U. A U represents our universal set. So think of that as representing all the elements that we care about. So in this particular setting, for whatever reason, the only elements that we care about are A, B, C, D, and F. And then within that universe, we've got a couple of other sets that are given to us, sets A and B. Based on that, we're going to find a few different things. So part A, we're going to find the complement of A. So keyword for the complement is not. So you're just listing out which elements are not in A, but in order to do that, you have to have a sense of what your universe is. So given that A, B, C, D, F are the only elements we care about, which of these elements are not in A? Well, little a, little d, and little f. There we go. So that's our complement of A. Part B, let's find the complement of A union B. So there are going to be two different operations we're going to have to do here. Order of operations tells us we should work inside the brackets first. So we'll first figure out what A union B looks like. And then once we have that in front of us, then we can take the complement of that set. So A union B, remember keyword for the union is or. So you just want to write down all the elements that are in A or B or both. So that would be B, C, D, F. And again, it doesn't matter what order you write down the elements in, but you should have these four elements in your set in some order. Okay, now we're going to take the complement of this thing. So let's just go systematically through our universal set here. We'll just write down all the elements that are not in A union B. So that would be just A. So even if you're just writing down a single element, you still want set brackets around that so that that's written as a set. So part C, we're going to find the complement of A union B. So this time the order of operations would be to first calculate the complement of A, and then once we've got that in front of us, then we can take the complement of A and do the union with B. All right, so complement of A, we actually talked about that in part A of this problem. You're just writing down all the elements that are not in A, but that are in the universal set U. So that would be A, D, and F. And now we can just highlight the complement of A, and we can highlight B. And the operation that we're going to perform on these two sets is the union. So you're just listing everything that's in the complement of A, that would be A, D, and F, and anything else that's in B that you haven't already written down. So that would be the element C as well. And then as usual, you can give your answer in any order that you like. So if you want to rewrite that in alphabetical order, that's totally fine. That's just an alternative way of giving the answer. Last piece of notation that we need for this section, we sometimes want a symbol to describe that an element B is an element of a set A. So the way we're going to express that is just with this letter E here. So B is an element of set A. We write it like that. So let's do a quick example just to practice that notation. So you could say -1 is an element of the set -2, -1. So notice that when you're writing down an element, you're not using set brackets. And when you're writing down a set, you are using set brackets. So you'll always see something of the form symbol is an element of set. Compare this with our subset notation. So we could say the set -1 is a subset of -2, -1. So if you're using the subset notation, you'll always see a set is a subset of some other set. So it's good just to distinguish between those two pieces of notation. Okay, if we wanted to say -3 is not in the set 4, 5, we could say -3 is not an element of the set 4, 5. The set -3 is not a subset of the set 4, 5. We could say the number 1 is not an element of the empty set. Remember, the empty set contains no elements. And we could say 0 is not an element of the empty set. Again, the empty set has no elements, so nothing is in there, not even the number 0. So that is our introduction to sets. We looked at a few operations we can perform on sets and the notation that goes along with that. So we'll be focusing on sets in chapter 3, and then that's going to set us up to get into probability in chapters 4 and 5. Thanks for watching.